Hi, this is Module 17 of Applications in Engineering Mechanics. Today we're going to finish up that bending moment diagram that we started last class. And so this is where we left off. And so at this point D, we're now looking at the change in the moment between point D and point E. That's equal to the area under the shear curve. The area under this rectangular portion of the shear curve is positive 15,000. And so we're going to go from a value of minus 3,000 up to a value of 12,000. And this is obviously not quite the scale, but I'll do my best. The slope of the moment diagram is equal to the value of the shear, which is constant all the way along, and it's positive. So we're going to have a constant slope from here to here. So that's a straight line. Now in going from point E to this point where we have zero shear, the area is a triangular area that's equal to 3,125. It's positive shear, a positive side of the shear diagram. So that means we're going to go up another 3,125, or we'll be up to 15,125. And there we're integrating a ramp, so that's going to be a parabola shape. So our slope goes from some positive value to a value of 0. So we're going to go positive up to a value of 0. That should be a parabola type shape. So I'll label it as a parabola. And finally, in going from that point to the end of the beam, or the pinned part of the beam, we have a area under the shear curve to be negative 15,125, which means we're going to drop down 15,125, which brings us back to 0, which again, it always should. That's a good way of checking yourself. In this case, again, we're integrating a ramp, and so that's going to give us a parabola. So if I draw that in here, it goes like that as a parabola. And we've completed our moment diagram. So now I have a complete depiction of both the shear force and the moment anywhere along this beam. I don't have to cut it in several different places to find out what the shear and the moment is at each of those places. I know it all the way along. And so, like I said in my earlier module, I noticed that the critical values for shear are at 10,000 over here, minus 10,000 over here, 11,000 here, 11,000 over here, a little less in between. The values where I'm going to have the most moment, and we're going to have to be critical in designing the member to hold those loads, are here at point C at the roller, where we have a value of minus 30,000 pound-feet. And we have a positive value of 15,125. But this section over here is where we're experiencing the largest moments. So very, very helpful diagram. It will be very, very useful as you proceed in future courses in designing beam members and mechanics of materials. Okay. Just like playing a piano, the way that you get good at engineering problems is to practice. It's a skill-based thing, and so you have to practice over and over again. And I've got some worksheets for you to work out. I always like to tell my on-campus students that it's easy to watch me do the problems because I've been doing them for several years now. But just to watch me do them and not practice on your own is not a good way of learning. The analogy is my oldest daughter used to be able to run an 18:30 5K race, which is very good. And so I could watch her all day long, but I couldn't get that fast. I'd have to practice and practice and practice. And even when I practiced, I couldn't get below 20 minutes for a 5K. But I got better by practicing. And so that's what you need to do with these problems. Here's a worksheet with a simple beam with a roller on the left, a pin on the right, and a loading situation. I've got the solutions to all of these worksheets in the module handout, so you can check yourself out. This is a cantilever beam situation with an applied moment on the left-hand side and an applied force in the middle. And then finally, another cantilever beam. And you can neglect the weight of the beams in all of these worksheets and just use the applied loads that I've shown. So after these series of modules, you should be pros at doing shear force and bending moment diagrams. And we'll pick up next module with structures that are supported by cables.